Hi, welcome to the. In this lecture, we are going to be looking at two important concepts. Firstly is to understand the general architecture of a simple microcontroller, and secondly, how we can read and write to devices using general purpose I/O pins. We are already familiar with GPIO pins from our Arduino sketch programming, but in this studio and in this e-lecture, we're going to be exploring how we can perform GPIO programming using the bare metal or low-level register programming. So before we get started on that topic, let's get familiarized with ones and zeros. Now, a binary system is the most basic system used in computing and in programming. Everything is represented in ones and zeros. Ones and zeros are what we call logical representations, but they actually translate to physical voltage signals. For example, if I were to connect, for example, port B pin 2, okay, and I connect it up to a LED, and I write a logical 1 to it, I expect this LED to light up. Okay, and why would that be so? Because that logic 1 actually provides me with a particular voltage at this pin. Now, what voltage would I expect? If my microcontroller is running on a 5-volt supply, then I would expect the logic 1 to be also 5 volts. If my microcontroller is running on a 3.3 volt supply, then the logic 1 would also be 3.3 volts. So the 1 and 0 logically does represent physical voltages at the microcontroller output pins. In terms of binary representation, a bit is always referred to as either 0 or 1. In most cases, we can also refer them as false or true. The other popular units that you will come across are bytes and words, where byte is 8 bits, okay, and nibble is not fixed because it depends on the architecture of the computer system. So in some cases, it could be treated as a 1 byte, 2 bytes, 4 bytes, and so on. Okay, the nibble, which is a 4-bit data, is very rarely used, so we don't need to be concerned about that. N bits can represent 2 to the power of n values. Okay, so when depending on number of bits that you have, you will know how many different values I can actually represent. So for example, if I have 3 bits, 2 to the power of 3 gives me 8. So I have 8 different possible values. Okay, you can also think of the reverse manner, where if I have to represent m values, how many bits do I need? Okay, and to do that, you can use the formula log to the base 2m. If the m values is already a direct result of a 2 power, then is no problem. So for example, 32 is actually 2 to the power of 5, so I need 5 bits. 64 is 2 to the power of 6, so I need 6 bits, and 1024 is 2 to the power of 10, so I need 10 bits. But how about 40 and 100, which are not direct 2 powers? Then I apply the formula log base to m, and then I take the ceiling function. This ceiling function means the round up to the next integer, and that will give me the number of bits that I require for that number of values. All our life, we have been exposed to the base 10 number system. And how does it work? For example, if I write the digit 9, this is a ones, okay, a single digit by itself, so we say it is 9. If I were to write a 1 beside it, then the 9 is in the tens position, so I say it is 91. But if I write another digit beside it, then the 9 goes to the hundreds position, so I say it is 912. So the same digit 9 takes on different values depending on the position that it takes within the actual number. That is why we call it a weighted positional number system. Okay, so the actual value, as you can see, for 912, it is 2 multiplied by 10 to the power of 0. So I start off with power 0 here, then go on to power 1 and power 2 and so on. So that is how I get the actual value. 10 to the power 0 times 2, add with 10 to the power 1 times 1, and 10 to the power 2 times 9. So I eventually get 912. Okay, so effectively what I'm doing is I'm getting the actual value by the position, which is in the ones position, tens position, hundreds position, and so on. Now this same principle can also be applied to base 2 systems. For base 2 systems, I do the same thing. So I now say this is 1 multiplied by 2 to the power of 0, this multiplied by 2 to the power of 1, 0 multiplied by 2 to the power of 2, 2 to the power of 3, and so on. Okay, so it is the same idea that I now apply, but now the base is now 2. Okay, and that allows me to find the actual value. Now, how do I convert between hexadecimal and binary? It is a simple, straightforward process. All I need to do is to group them into bits of 4. Now, uh, before we go there, what is hexadecimal? Hexadecimal is also another number system that is very common in computing. In hexadecimal, you have a base 16, that means 16 different digits. And the 16 different digits are represented by numbers 0 to 9, which are the 10, first 10, and subsequently A to F, which are the remaining 6. Okay, and how do I convert them? I convert them by grouping them into groups of 4. So from hexadecimal, okay, for example, to binary, I convert each of the hexadecimal bits into the equivalent 4-bit value. So 3 is 0011, E is 1110, and 1 is 0001. So that gives me the actual binary equivalent. Okay. If I were to do the other way, from binary to hexadecimal, again the same thing. So for example, this 111001, I group them into groups of 4, starting from the least significant bit on the right. So 1, 2, 3, 4. So this is one grouping. So this gives me 9. And this, I only have 2 bits, so I can pad another 2 zeros in front, which will give me 3, so 39. Okay, so this gives me the hexadecimal representation. Okay, given any number, how do I know whether it is in represented as a hexadecimal or decimal or binary? To do that, I need to be familiar with the naming conventions. So one of the common naming convention is to put the base at the end of the number. So base 2 or base 16. The other one is to put the alphabet. Okay, so B or H. You can also put the alphabet in front, 0B or 0H. And the last option is 0X, which is also supported by many compilers, okay, when you are writing it in C. Okay, so these are the different conventions which you will also come across in many reference textbooks and online resources, okay, when you are looking at binary and hexadecimal numbers. An important operation that you need to do when you deal with embedded devices is bitwise operators. Why is that so? Because in microcontrollers, you will deal with a lot of registers. A register is nothing more than a group of bits. Okay. In some cases, the registers may hold actual data, so you look at the 8-bit as a whole. In some cases, for example, very often in status registers, different bits may represent different information. So for example, bit 0 in this case may represent whether there is any error in the device. Okay, bit 2 for example will tell you whether you have received anything. Okay, bit 3 for example will tell you whether you are going to transmit anything. Okay, I just give you an example. Okay, so every bit within a register may give you different information. In that case, you want to just extract out that particular bit, okay, and ignore the rest. So you can achieve that by performing bitwise operations using the AND or NOT operators. And how do we go about? It is to create what we call a mask. Okay, and there are two basic operations you want to do. Either you want to clear a bit or you want to set a bit. Okay, to clear a bit, what we need to do is to create a mask where that particular bit is 0 and all others are 1. Okay, and then we do the AND operation. Okay, so for example, I'll take this register here. Okay, let me put in some values. Okay? So this is bit 0, bit 1, bit 2, bit 3, 4, bit 5, bit 6, bit 7. Okay, so let's say I want to just clear this particular bit. So to clear this particular bit, I must create a mask where that particular bit is 0 and everything else is a 1. Okay, so that would be the mask. Okay, and then I do a AND operation. Okay, so this is to do the clearing. How about setting a particular bit? To set a particular bit, I create another mask. Okay, but in this case, that particular bit will be set to 1 and everything else is 0, and then I do the OR operation. Okay, and this is to set a particular bit. And why does this work? Because when I AND with a 0, okay, I do AND operation with a 0, that particular bit will automatically become 0. So I'm clearing that bit. When I do it OR with a 1, that particular bit will become a 1 regardless of the original value. Okay, and by doing an AND with a 1, nothing else changes. By doing an OR with a 0, also nothing else changes. Okay, so that can be seen a bit more clearly here. Okay, where I want to clear bit 3. Okay, so this is the mask. So that particular bit position is 0. Okay, and that 1 will become a 0. If I want to set bit 5, then I create a mask where that particular bit is 1. So the output of that bit will become a 1. This is the C code to accomplish what we just saw. Okay, so you can try this out in your Arduino programming. Okay, now let's look at the Arduino embedded board that we have, the Arduino Uno. Okay, so this is the full schematic of the entire development board. But if you look closely, the Arduino Uno is actually just that one single chip. Okay, there are a lot of things that you see on this slide here, but if I want to create a standalone Arduino Uno device, I only need this particular chip, which is the ATMEGA 328, together with the connections for the power, okay, the reset pin, as well as the crystal. Okay, basically once these three subsystems are configured correctly, the entire system can be a standalone. Okay, and you can reduce the footprint to a very small area. Okay, much smaller than your current Arduino Uno board. Okay, so these are three important things that you need. Okay, if you want to create a standalone embedded system. In terms of the architecture and the features, this is a 20 megahertz device. That means that is the highest clock frequency at which you can run it. It is a 8-bit microcontroller. Okay, when we say 8-bit, it means that the registers within the microcontrollers are 8-bit. Okay, so you can perform 8-bit computation at any point of time. Okay, then there are also some registers. We don't need to be concerned with this because when you code at the higher level of C, which registers to be used is sort of taken care of by the compiler. Okay, so this is transparent. And what we're interested in is, of course, all these peripheral options. Okay, so as you can see, we have a vast array of peripheral options in terms of GPIO pins, A to D, PWM, counters, timers, UART, serial interface, and so on. And there seems to be so much of functionality, but yet the chip is not so big. Okay, so how is this possible? This can be seen in the next slide. So as you can see here, each pin, except for the power pins, almost every pin has either 2 or 3 functionalities. Okay, so there is one functionality / another functionality and so on. And what does that mean? That means I can select this pin, for example, pin 23, to operate as either a to D channel input, okay, or as a normal port input, okay, and okay, for the port C functionality. So I can vary between ADC functionality or port C, which also supports the interrupt feature. Okay, so every pin has a multiplex features that you can use. Okay, and you need to sort of configure the registers to ensure that you select the correct functionality for the design that you have. So that is how we are able to squeeze so much of features onto a small chip. Okay, because not all the features can be used concurrently. Okay, you need to make a conscious decision on what you want for each pin. Okay, this is an important slide because Up till now, when you're doing sketch programming, you are dealing with this Arduino pin numbers. Okay, but these Arduino pin numbers, of course, are easily relatable because they are brought out directly to the connection headers on your board. But internally, they are connected to ports and pins. So when you do low-level microcontroller programming, you need to be familiar on exactly which port you're dealing with, and within that port, which pin you're dealing with. Okay, then you can provide the correct low-level code to configure the I/O pin. So GPIO programming is the most important and fundamental peripheral programming section that you must complete first whenever you are going to deal with a new microcontroller. This just gives you a snapshot of the internal structure. As you can see, the pin is actually just a single physical device, but at the background, within the chip, there's a lot of logic gates here. Why? Because of the multiplex nature of each pin. So every pin, there's a lot of built-in features, so we need to make sure that the correct features are enabled depending on our settings. So that is why you have a lot of internal hardware for each pin. In the ATMEGA 328, we have 3 GPIO ports: port B, port C, and port D. Okay, and we need to configure them according to our needs. Okay, how do we go about doing that? For GPIO programming, the first thing is the direction, and that is achieved through the DDRX register, where X is either B, C, or D. Okay, so if I want to configure DDRB register, port B register, then I configure the DDRB and I select the appropriate bits to be either input or output. Every microcontroller has its own convention. In ATMEL microcontrollers, a 1 to the DDR register means it's output, a 0 means it is a input. Okay, so this is specific to the microcontroller. If you were to play with or use a different microcontroller later on for some other project, then you need to look at the datasheet again, okay, to know what is input and output. Okay, once you set the direction, the next thing is you can either write to it or read from it. To write to a pin, you need to update the port X registers. Okay, so if I want to write to a port B, then I directly write to port B, and putting a 1 or a 0 will give me the equivalent voltage at the output pin. Okay, how about reading from a pin? To read from a pin, there is a different register. That is the pin X register. So when I want to read from a pin, I need to read from the pin X register to know the value. So for example, if I want to check whether port B pin 3 is being set, what I can do is I can read from pin B and I end with a mask. And as you can see in this mask, only bit 3 value is set to 1. Everything else is set to 0. That means I am going to discard all the other bit values and I'm going to only look at port B pin 3. So the result that I'm going to achieve is either going to be 0 or non-zero. Okay, if port B pin 3 is 0, then the whole result is 0. Okay, if port B pin 3 is a 1, then the result is non-zero. Okay, because that pin will be retained after the masking operation. So that is how I'm able to check whether a particular input pin is set or clear. So this is an example of LED lighting, okay, which you will do in your studio. In this code, you can see that I first set the DDRB register, followed by changing the port B values to either on or off the LED. In the second example, we are going to read first from a pin, okay, which is a switch, and then finally use that value to decide whether the LED should be on or off. Okay, so in this example, the first step is to configure the directions. Okay, so one for the switch and the other for the LED, and subsequently I check the status of the switch, okay, by using an appropriate mask, and then subsequently I either on the LED or off the LED. So you'll be trying all of this in the studio, okay, to give you some hands-on experience. And that brings us to the end of the e-lecture. So I hope that through these slides you have got a good glimpse of the number systems, the microcontroller concepts, as well as how to program GPIOs at the register level. Okay, and I hope it will be a good start for you for the studio. Thank you.